Hello, good morning, good afternoon, or good evening, whatever time you're watching this educational video. Tonight, I will introduce a problem about work and conservation of energy. We will integrate these two concepts in finding one variable. If you can have other way to do it, yeah, you can freely comment on the comment box of this video. So here's the problem. We have 58 kilogram skier. That's the mass of the skier coasting down or moving down or motion down all the way to this 25-degree slope. There's an elevation around 25 degrees rather. And then a kinetic friction force of 70 Newton. It's calculated already. It's 70 Newton according to this problem, so it's going to be negative. Negative here is the direction. It it doesn't mean that it's a lesser value, but it's just the direction. It opposes the motion as stated in the problem. Near the top slope, above the slope, the skier's velocity is 3.6 meter per second. Ignoring air resistance, figure out the final velocity at a point that is displaced by 57 down. So I'll be showing you the vectors involved in this problem. I created here a vector from initial position. The skier moves down all this up to all this position here, and then this is a slope, and it's elevated around or at 25-degree angle. And in your bank curve, if you will have an elevation here with respect to the horizontal, this is going to be equal to this angle here. Okay. And then if you notice that you will have a friction force here opposing to this vector here, this arrow going down all the way to the final position of the skier. And the skier is being attached or being touched by the ground or slope floor. So the force involved here is normal force. It's the force that is attached perpendicular to the object and the ground itself. So the arrow is just like that. Okay. And this time it is not balanced by the weight force here because the weight force is in this direction. Look at this vector here. But the component of the weight force is the one balances the Fn, and that's the y component of your mg force. Here is the y component of the mg force, and this is going to be the x component of the uh, mg force. So if you notice, the y component of the weight force carries the cosine theta because it's adjacent to the angle. The side is adjacent to the angle, so it carries the cosine theta. And then the opposite angle, the opposite side here, it will carry the sine theta. And don't forget that this vector is equal to this vector here. And obviously, this x component of the mg is equivalent to this x here. So the value of this vector is equal to the mg sine theta. So that's why I put it here, mg sine theta. It's equal to this vector here, the x component of the weight vector. Okay, and this mg sine theta, always remember mg mass times the gravity, that's equivalent to the normal force or Fn. Okay, so Fn sine theta, that's the value of this downward force here, like going down on a slope. And it is being opposed by the friction force. To be specific, it's the kinetic friction. Okay, so we have the value now, not yet the value, but we have the variable for the downward vector, and we have fk for the upward or the opposite vector of the mg sine theta. And a displacement from original position to final position, it's given in the problem, it's 57. And the initial velocity from the top, according to the problem, it's 3.6 meter per second, and we need to find the final velocity here. Again, our task is to figure out the final velocity. The first thing we will do is to identify all the forces along the x-axis. X-axis is this line here. And if you notice, we only have two vectors there. We have the mg sine theta, and we have the friction force, the kinetic friction. Let's be mindful with the direction of these vectors here. If it's going up, left side, it's going to be negative, and it's going down, right side, it's going to be positive. So again, I will just repeat that the x component of the mg force is equal to this one, and of course, to the arrow going down earlier. It's equivalent to Fn sine theta or Fg sine theta. So again, we will plug in here all the forces along the x-axis. We have positive mg sine theta. And we have negative Fk or kinetic friction because it goes here in this direction. Let's substitute all the variables or the values of these variables. 58 is the mass of the skier. 9.8, that's the gravity's value. We have the sine 25, and we have minus 70 as as stated in the problem. It's 70 Newton opposes the motion. So that's the kinetic friction. If you will multiply this variable here, 58, 9.8, and sine 25 in your calculator, it will give you a product of 240.22. Minus 70, it will give you a difference of 170 newtons. This force along the x-axis, the sum of the forces along the x-axis, we will be using that one in determining our work done. To determine our work done, the simple equation is work is equal to force times displacement cosine theta. A little review. If the forces vector is having the same direction with its displacement of the object being applied by certain force, it will create a zero angle. So cosine zero, that's 1. So we will have a positive work in that case. Or let's say if it's going down, if gravity does all the work and the displacement is downward, still that's zero angle since they are parallel with each other. And cosine zero is 1, positive 1. It will make the work becomes negative if ever that we have opposing vectors. For example, the displacement is going to this direction, and then the friction force is opposing this direction. So it will be forming a 180 degree. And if you will input that in your calculator, it will give you a negative value, a negative 1. Cosine 180 is negative 1. So we will have a negative work in that case. And of course, if the vectors are forming 90 degrees, that's zero work because cosine 90 is 0. And in this case, no right angles, or I mean, no, yeah, the vectors are not forming right angles here, so our work is not 0. But this time, the downward total force and the displacement is going down. They are in the same direction. So the value of this cosine theta will be positive because it's parallel, 0 degree, no angle being measured since the vectors are moving in the same way. So we can just delete this part, cosine theta, because cosine 0 is 1. You will just multiply 1 to this variable. The same answer um, will be determined. So the force, we will be using 170 from the forces, net force in the x-axis, and we have 57 as the displacement according to the problem. And we have cosine 0, that's going to be 1, right? So 170 times 57, that's 9,690. Multiplied by 1, it will give you 9,690 Newton meter, or you can have joules. That's the amount of work in this scenario. Now, the problem wants us to know the final velocity from this position all the way to this final position. Okay. So in doing that, we will incorporate the conservation of energy. Work is equivalent to delta, or change in kinetic energy. We are using the kinetic energy here because kinetic energy, uh, the formula for kinetic energy is 0.5 mass times velocity squared. So the velocity variable is hidden in kinetic energy. It's moving, so it's moving, so it has a velocity going on here. And we arrived to this simplified formula. Remember, try to look at this. Work is delta kinetic energy. So it's the change in kinetic energy. So work is equal to kinetic final minus kinetic initial. And we will transpose this kinetic final here because we want to isolate the V final. It's hidden in that formula. Okay, the velocity in KE final, that's the final velocity. And the work also, we will move it here. The sign will change as well from positive to negative. So we have negative KEF, negative work, and negative KE initial. To let our variable be positive, especially the KEF, we need to multiply both equations by negative. So negative and negative, that will become positive. And then negative multiplied by negative work, it will become positive. And the negative multiplied by negative, that's positive. So that's our equation being derived. And kinetic formula, as I said, there's a variable of velocity there. It's equivalent to 0.5 mv squared, or 1/2 mass times velocity squared. The KE final, once again, it hides the V final. Kinetic initial, it hides the velocity initial. Let's go back to the solution. There you go. I showed you how we derive in this equation here. In that case, you will have KEF is equal to work. The work done is here, 9,690. So we plug it here in our variable work. And we extracted the formula for KEI. We have 0.5, that's the formula of kinetic energy initial. 0.5 times mass times velocity initial, and then squared. We can also do it this way on the other side, the KEF, but this time it's the final velocity that we need to find. So we have 0.5 times the mass of the skier, 58. This is the work done we calculated a while ago. And we have 0.5, 58 the mass, and 3.6, that's the initial velocity according to the problem, initial velocity. and it's gonna be to be squared later. So we have 0.5 times 58, so you will have 29 v final squared, and we have the work plus the value of this. It's equivalent to 0.5 times 9.8 times 3.6 squared. That's equivalent to, hold on, 0.5 times 58 times 3.6 squared. So that's 375.84. And we will add it to the work that we calculated a while ago. It's 9,690. It will give us a value of 10,065.84. I never put it there, but yeah, you can just add it. You will arrive to that sum. 10,065.84, and we will divide both equation by 29. We'll have a value of our v final squared 347.10 rounded. Okay, again 347.10, and we will get the square root to isolate the b final. So we will have the square root also on the other side, and then our b final is 18.63. That's the answer. And there is another way to do it. Okay, another way to solve for b final. If you like this one, you can also use it. Again, from this equation, work is equal to delta, or change in kinetic energy. So we have KEF minus KEI. That's the change in kinetic energy. It's equivalent to work done. And we polish it. We multiply both sides by negative, so we will have this one. Okay, so determine the final velocity by using this derived formula here. Its final velocity is equal to 2 times the kinetic energy final divided by the mass. So get this value because we need this variable here, KEF, in our formula to get the speed, or the final speed or final velocity. So the work done earlier, we have 9690 plus all the factors will be multiplied. It will have 375.84 plus 9690. You will have 10,065.84. This is the value of your KEF. So we will substitute here in our derived formula. So we have 10,065, and we put it here. We plug it here, and times 2 divided by 58. That's the mass. So you will have 20,131.68. 20,131.68 divided by 58. You will have this expression inside the square root. Okay, 347.10. Get the square root, and that's gonna be 18.63. Same velocity as we had a while ago. So that's it for tonight. Thank you so much. I hope this video helps you in your review. See you around till next time. Bye for now.